welcome to the next video in the systems programming video series. In this video, we're gonna look at memory. I think a lot of us tend, especially early on in a computer science degree program, to think, and correctly think, that algorithms are the most important thing for getting your program to run correctly and quickly, right? Especially we're interested in the asymptotic runtime of algorithms, and all of that is completely correct. But certainly in the day-to-day life of a programmer, it will become important to get the memory right as well, right? It's maybe not the most important thing, but it certainly is important enough that your job can depend on it, so we should talk about it and make sure that we get this right. And it also depends on exactly what you do with your computer science degree. Certainly if you are going into some kind of a field with sort of industrial or commercial applications of computer science applications, then this stuff can be especially important. And if you go into other areas, then it can be less important. But anyway. But the important point, especially for us right now, is the concept of memory locality. And this is the idea that memory, which is located close to the CPU, runs especially fast. The CPU is small, it is lightning fast, it can only hold so much data. So you get a more performant program if you strategically locate data close to the CPU. And this is illustrated by this example, which is essentially, algorithmically, this is effectively the same program, basically, right? At an algorithms level, what both of these two programs do is take some matrix and iterate over every row and column, sum them all together, and then at the very end, compute the average. So this one, the second one, does exactly the same thing, and there is only one subtle difference, which is that rather than doing it in a so-called row major way up here, this one does it in a column major way. And so what does that mean? Well, here we take we pick a row, and then we progress, right? That every next thing that happens after we select this row is that we select the next column in that row until we reach the end, and then we increment the row. That is row major processing. This is column major processing in that because the I index is chosen first, then we here are selecting the column I, and then progressing down the rows, progressing along the rows for a fixed column. Well, when you think about how memory is organized physically on your computer, a given row is all located close together in consecutive addresses in memory. And what that means for how a computer tends to organize its information is when you ask the computer to access the information at coordinate ij, it actually tends to take addresses which are close to that coordinate and puts them all together on a bus and moves that bus of information close to the CPU. So it doesn't just grab the one piece of information from, say, DRAM or whatever, moderately slow, but not the slowest. But in any case, right, it doesn't just grab that piece of information from some memory as a single bit of information or byte of information or whatever it might be and move it over to the CPU where it does some computations. That's not what happens. Instead, because it just tends to be that data which is close together tends to be needed together, then it actually grabs all the information around that address in memory, puts it all together on a bus, and moves that whole bus over close to the CPU. Well, here, what's going on is that we grab a row, and that row, all the data in the row is close together. All of that close together information all gets moved together. And that moving, right, that busing is a costly operation. So you want to do it as little as possible so that all of that information gets put on a single bus, shipped over to the copy of the data close to the CPU, and the CPU runs very quickly on that bust-in information. Over here, by contrast, we get the IJ coordinate, right, some particular location on some row. The whole row gets, again, right, just because rows are kept close together, that row gets moved over close to the CPU, but then we only use a single value from that row. And the rest of the bust over information just gets wasted because we're not using it in the next step. Well, what happens after that? Because the cache that is on the CPU, where cache received all that bust over information, it's on the very next increment of J, we move to a new row, which means that we have to go a whole new bus of information over to the cache on the CPU. And it doesn't have a lot of space, so the previous row that you bust over has to get deleted, right? You pulled in all that information that was going to get used at some point, but then you just threw it away and bust in the new row, a single value, and then bust in a new row, and right, you're calling the bus so many more times because you're going in a column major way and not using the information that gets bust over when it's sitting right there on the cache. So that's why the second variation runs so much slower. And I'll let you read the textbook to get more details. But the important point is that this is just an illustration of how the memory on a computer is organized. This is called the memory hierarchy. And the closer it is to the CPU, the faster it runs. So registers are right on the CPU, and they are lightning fast. Cache is only a little less fast, but still very fast. It is also on the CPU, but there's more cache than there are registers. There's I think you can write all the registers on less than a sheet of paper, right? There's not many of them at this fixed, rigid, small quantity of registers. So they can hold information, but not a lot. But they are so fast, right? Cache holds more. It's a little slower. Main memory, I think, what are we calling main memory? This is primary storage, so that would be RAM. Is it SRAM? Is it DRAM? Certainly DRAM would go here, and SRAM, I'm not actually sure, honestly, whether it would go as some kind of very low categorization towards the bottom of the cache in this pyramid, or would it go just as a high place in memory. I'm not sure exactly where SRAM lies on this diagram, but it's somewhere in this region. Anyway, it's not the most important thing. We're not going to need these details. In fact, I should probably mention, everything that we're talking about here right now, we're not really going to use in the programming assignments and stuff like that, but it is for contextual awareness, so that you understand why we're doing the things that we do in the programming assignment. But it's mostly for motivation and understanding, but not so much for actually completing the technical requirements of homeworks and so on. So anyway, and I guess what is also worth pointing out is that as you go down this triangle, the things that are farther from the CPU tend to have much more capacity in terms of just how much memory, how many bytes can they store, and so on. And that's a very typical trade-off, right? Because things that are very, very fast are typically very expensive per byte that it can hold. So you'd love to make a computer all out of registers, right? Every bit of data on your entire computer just has CPU almost right next to it. But that's just cost. The cost of doing that would exceed the GDP of a wealthy nation. So you can't do it, right? So you have to compromise by having cheaper storage, but then you can have so much more of it. So, okay. By the way, cache is actually split into different levels. Now, different computers are different, but most computers have a level 1 cache, which is right up the top of the pyramid, kind of, and is very, very fast, but it holds less, as the theme of this tends to go. Level 2 cache is a little bit further away. And then almost all computers these days are multi-core, so almost all computers these days have a level 3 cache, and this is not only farther away from the CPU and a little bit slower, but holds a little bit more. But in fact, there's another distinguishing character of level 3 cache, which is that it is shared between certain cores on a chip. And so that gets you into the whole topic of multi-core processing, which will come up shortly, but for us right now, we're not going to worry about it. In fact, for us right now, we're mostly going to just pretend like there's no distinction between the levels of the cache. Anyway, on to the next section in the next video.